Greetings, physicists. This lecture will be about angular momentum and the conservation of angular momentum. So let's take an object. Use a rod. It's not even a uniform rod, that's okay. Let's give it a hinge. It'll rotate about that point. And let's apply a force to it. And that force is at some radius r. And we know that if we apply that force at that radius r, assuming there's no friction or anything, that there will be movement in this counterclockwise direction because I will have applied a torque. And we know that equation. That equation is the torque that I apply should be equal to the moment of inertia of that rod times its angular acceleration. Well, we can break that down by this alpha here. The alpha, we have an equation for that. Alpha was a change in angular velocity divided by the time period, so the rate of change of velocity with time. So if I stick that back into the torque equation, I'm going to get this. Torque will be equal to the moment of inertia of the object times the change in its velocity divided by the time interval. And now just to equalize things here, not equalize, I'm just going to multiply by delta t on both sides. That'll cancel it from here. And I will get this equation, which should look familiar to you, which is torque times the time interval is equal to the moment of inertia times the change in angular velocity. Notice the parallel between this formula and this formula. So this is the impulse momentum equation. We had the impulse on the left side, and we had change in momentum on the right side. We use P for momentum. That's linear momentum. Well, what we're seeing here is that for an object that rotates, there's going to be basically the same form, right? Force and torque are analogous, mass and moment of inertia are analogous, and angular and linear velocity are analogous to each other. So we're going to say that this torque equation, torque delta t equals I delta omega, that is going to be our angular momentum or impulse momentum equation. And so I'm going to create a term for angular momentum. It's going to be this, L. L will be angular momentum. And for linear momentum, it was P equal mv. For angular momentum, it's going to be L equals I omega. So exactly analogous to linear momentum. And so this equation up here, this on the right side, has change in angular momentum. So on the left, it would be, I guess, like an angular impulse. And just like regular momentum, we had a conservation equation. In regular momentum, because when things interacted with each other, F delta t was always the same, right? There's equal and opposite forces, and for the same time interval. The same will be true when things occur, when we have an angular impulse. In other words, we'll say that angular momentum is conserved, or that torque times a delta t will be equal to a delta L. But that the amount of, for instance, if you had a spinning disk that's spinning one way, and you were to drop it down on top of another disk that was not spinning, and they stick together, and so you have, let's try and draw this like a disk on top of another disk. they will now start to spin together maybe if they stick. So maybe this, I'll draw a shorter arrow here to indicate that the one on top lost some speed and the one on bottom gained some speed. Now they're going together. All right, there was a torque. There was a torque on the top one, there was a torque on the bottom, but they had to be equal and opposite. And so we could say that the amount of momentum gained by disk 1, the delta omega, had to equal the amount of momentum lost by disk 2. So we'll have kind of the law of conservation of angular momentum, which is very similar to the law of conservation of linear momentum. Or we could rewrite this to say that the I delta omega for disk 1 has to equal the negative of the I delta omega for disk 2. So if you have mastered linear momentum, we're really just changing the variables to look like angular variables, but all of the mechanics of equation solving should be about the same. So I'll just give you examples of things. The very common example is a figure skater. You'll see this all the time. You have, oh, let's do this. You have some figure skater, and they always stand on one foot when they do this, right? And they have their arms way out, and they spin, because that's pretty. And then what the figure skater does is they hunch their shoulders in, and they bring their arms in close while they're standing still, and maybe the leg is, oh, hold on, I did this wrong originally. Let's make the leg out to begin with. You know how they do those cool pirouettes? Here, this is actually a better, yeah. So he's spinning with his leg out, then he tucks the leg in, crosses it maybe, and now he's spinning like this. And they seem to go faster. Like they seem to spin, if I could even draw that. So yeah, he's spinning even faster in a circle when he tucks his stuff in. Why would that happen? Well, he had, in this position, some initial angular momentum, some initial moment of inertia, and some speed. So you could say that the I omega in this position was equal to his angular momentum. And it could be omega 1 and then I1. And then later, he has some new moment of inertia. His moment of inertia will change because the shape of his body has changed when he tucks the arms in and tucks the leg in, times his new angular velocity, and that would be, so that's L1, and that would be his L2, his angular momentum. So he has some angular momentum in position 1 and some angular momentum in position 2. But as long as this is a closed, isolated system, he's not losing any momentum. He's just tucking his arms in, right? He's not pushing off the ground or something and causing an extra torque on himself. So without a torque on this system, without a net torque, I should say, on this system, the angular momentum should be a constant. So I should be able to set the angular momentum from the first position equal to the angular momentum of the second position. And if I do that here, I should have the I omega 1 equal to the I 2 omega 2. So let's think about this. What we definitely see in the second position is that omega 2 is faster. We see a faster moving skater, spinning skater. Well, what must that mean? In order for these things to be equal, if this is bigger than this, if the right omega 2 is bigger than the left omega 1, then the right moment of inertia should be less than the left moment of inertia. And that should make some sense, right? That on the left-hand side, he was all spread out, hands way out here, feet, while he was spinning. And on the right side, it was all tucked in, his foot over like this. And our basic moment of inertia equation is mr squared. Now that's mr squared for every point of mass that he has. And but if you look in general on this side, all of his mass is at a farther radius from his center of mass, and over here all the points are not all the points, a lot of them are in the same position, like his spine has probably not changed much, but all of his arms and legs have generally moved closer, so that R value should be smaller over here. The mass should not be changing. So we're essentially taking all of his mass, moving it closer in, and that's going to make the I over here, I1, bigger than I2. So you can kind of see that there. If this omega gets larger, that's because this I got smaller. That's a conservation of angular momentum. Okay? So that's the basis. You're just taking the old impulse momentum equation and changing it to from a linear quantity to an angular quantity, and the old conservation of momentum equation and changing it from a linear quantity to an angular quantity.